Swayam Prabha. Digital India. Educated India.
Now, we will move to the division rule. Now, division rules, there are n divides d ways to do a task if it can be done using a procedure that can be carried out in n ways, and for every w exactly d of the n ways corresponding to the way w. So, that is the meaning of division rule. Now, let us see one example. How many different ways are there to seat the 4 people around the circular table, where 2 seatings are considered the same when each person has the same left neighbor and same right neighbor. Okay. So, we have to find out the different ways to be seated for 4 people around a circular table, right. So, we have to arbitrarily choose the table and label it seat 1. We number the rest of the seats in numerical order, proceeding clockwise around the table. Note that are 4 ways to select the person for seat 1, 3 ways to select the person for seat 2, 2 ways to select the person for seat 3, and 1 way select the person for seat 4. Therefore, totally 4 factorial ways to order the 4 people for these seats. Therefore, 4 factorial equal to 24 ways to order the given 4 people for these seats. However, each of the 4 choices for seat 1 leads the same arrangement. So, we distinguish 2 arrangements only when one of the people has different immediate left or immediate right neighbor, because there are 4 ways to choose a person for seat 1 according to division rule. Therefore, we have a 24 ways to given the 4 people divided by selecting the 4 person, we have 24 by 4 equal to 6 different seating arrangement of the 4 people around the circular table. This is a way we can find the one number divided from the others, counting the different seating arrangement of the 4 people around the circular table. Next, we will discuss tree diagrams using counting principle. How many bit strings of length 4 do not have 2 consecutive ones? How many bit string of length 4 do not have 2 consecutive ones? Now, we are going to see the figure. That figure displays the bit string of length 4 without 2 consecutive ones. Now, there are 8 bit strings of length 4 without 2 consecutive ones. Let us see through the diagram. Bit string start with 2 numbers, one is 0 and another is 1. Therefore, the first bit is 0 and 1, second bit is 0, 1, 0, not consecutive ones, right, like that. And then third bit possibility is 1, 0, 0, 1, 0, like that. And fourth bit from start 1 to 0, 0 having 1, 0, and 0 having 1, 0, and 1 having 0, 0 having 1, 0, like that. Because if 0 comes, it should be 1 and 0 comes like that. But 0 comes, whereas 1 does not come like that. Now, because 2 consecutive 1 do not have one another, then only we can have a tree. Now, based on this, based on this we have what this structure, you take it, we have what 1 0 1 0. Similarly, the tree having the branches 1 0 0 1 and then 1 0 0 0 like that. Here 0 1 0 1 and then 0 1 0 0 like that, and this one corresponding this. So, that 0 0 1 0 and then what 0 0 0 1 and then everything is 0 like that. So, that the possibilities of bit string is like that. So, this shows that the display of the bit string of length 4 without 2 consecutive ones. Therefore, how much 1 2 3 4 5 6 7 8. So, 8 bit string of length 4 without 2 consecutive ones. Now, this is a corresponding answer to the question. Now, let us go to the another example. We have a playoff between 2 teams consisting of at most 5 games. The first is teams that wins 3 games wins the playoff. In how many different ways can the playoff occur? Now, according to the tree diagram, we have to display the playoff can be proceed with winner of the game shown. Now, let us see, we have a game 1 consists of team 1 and team 2, and then team 2 consists of 2 team 1 team 2 and team 1 consists of another possibilities. So, this is possibilities of the game 2, and then team 2 having team 1 and team 2, and then this team 1 having team 2 and team 1, and this is possibilities of team 2 team 1 team 2 like that. This is game 3. Now, the winner is team 1 here, team 2 is the winner is team 2 like that. The different color, that is blue color, shows that the winner, and rest of them is playing like that. This team 1 having the possibilities of team 1 and team 2 game, and we have a winner is team 2, therefore, omit this part, and then team 1 having like that, team 1 as well as team 2 winner. The next we have a team 1 and team 2 is a winner, team 1 like that, it goes on. So, we have these are all the what possibilities of a winner of game 4, game 5 respectively. Now, you count it, the different colors, that is blue color shows that different ways of getting the winner, that is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 ways we have a playoff to occur the winner of the games. So, this way we can counting the what playoff game between the 2 teams, at most 5 games developed. Next we are going to discuss topic is the Pigeon Hole principle. So, Pigeon Hole principle actually is a very interesting one based on the pigeon, the nature of the pigeon, how they are sitting in the hole. Suppose that the flock of 20 pigeons flies into a set of 19 pigeon holes to roost, because there are 20 pigeons, but only 19 pigeons holes. At least one of these 19 pigeon hole must have at least 2 pigeons in it. So, the following pictures are more pigeon than pigeonholes, like that. To see why this is true, note that if each pigeonhole had at most one pigeon in it and at most 19 pigeons, one per hole could be accommodated. Now, we illustrate the general pigeon, call it as a pigeonhole principle, which states that if there are more pigeons than pigeonholes, then there must be at least one pigeonhole with at least 2 pigeons in it. See the figure 1. It shows that, see here, sometimes it may have a 3 pigeon, sometimes it has no pigeon, sometimes it has a 2 pigeon, sometimes it has 1 pigeon in one hole, like that. So, this way we have the principle, call it as a pigeonhole principle. So, from this what we can understand, the principle applies to any other object beside the pigeons and pigeonholes. So, keep it in mind this introduction of a pigeonhole. Let us go with one theorem, call it as pigeonhole principle. If k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more of the objects. So, this is the meaning of the statement of the pigeonhole. We have to choose the k positive integer and k plus 1 or more objects are placed in k boxes, that is most important, and then at least one box contains 2 or more of the objects. That is what we explained the previous introduction of the pigeon. Now, the proof is very simple. By using contrapositive in the sense that, contraposition in the sense that, assume one statement is true, then we have to prove a contradiction to our assumption that then it is to be contrapositive. So, the proof is based on the contraposition or contradiction principle. Suppose that none of the k box contain more than one object, the total number of objects would be at most k. Therefore, this is a contradiction because there are at least k plus 1 objects, hence the theorem. So, this way we can easily prove the pigeonhole principle. Now, we have a corollary. You take a function f from a set with the k plus 1 or more elements to a set with the k elements in not a one to one. So, obviously, the pigeonhole principle does not obey one to one mapping. One to one mapping means already we discussed a map f such that x to y, then x equal to f of x equal to f of y or not equal to f of y, then x not equal to y, or f of x equal to f of y implies x equal to y. So, using this condition, then it is one to one. If does not obey, then it is not a one to one, because all k pigeon does not occupy k cell. Maybe one cell can occupy 2 pigeon, one cell may be vacant, one cell may be 3 pigeon can occupy. So, these are all the possibilities. So, therefore, it does not obey one to one function, that is very simple. Now, we have a proof corresponding to the corollary 1, that is, for each element y in the codomain of f, we have a box that containing all elements of x of the domain of f such that f of x equal to y. Because the domain contains k plus 1 or more elements and the codomain contains only k elements, therefore, the pigeonhole principle tells us one of these box contains 2 or more elements of X of the domain. It means that F cannot be 1 to 1, right. So, it does not follow 1 to 1 function implies it follows more than one images from codomain to domain implies it is not 1 to 1, therefore, it obeys the pigeonhole principle. So, this way we can defense proof of the corollary 1. Now, let us see some more example of pigeonhole principle is used. Among any group of 367 people, there must be at least 2 with the same birthday because there are only 366 possible birthdays. Therefore, it follows pigeonhole principle. In any group of 27 English words, there must be at least 2 that begins with the same letter because there are 26 letters in the English alphabet. Another example, how many students must be in the class to guarantee that at least 2 students receive the same score on the final exam if the exam is graded on a scale from 0 to 100 points. So, the solution is there are 101 possible scores on the final. So, the pigeonhole principle shows that among any 1 or 2 students there must be at least 2 students with the same score. So, that is one of the examples of pigeonhole. Now, another example show that every integer n there is a multiple of n that has only zeros and ones in the decimal expansion. The solution is let n be a positive integer. Consider n plus 1 integer say 1, 11, 111 and then 111 up to n or n plus 1 digits. Now, last integer the list having n plus 1 ones in its decimal expansion, and note there are n possible reminders when an integer is divided by n because there are n plus 1 integer in the list. By pigeonhole principle, there must be a 2 with the same remainder when divided by n. The larger of these integers less than smaller one is multiple of n, which has a decimal expansion consists of entirely zeros and ones. So, this shows that examples of pigeonhole principle followed with every integer n there is a multiple of n that is only zeros and 1 in the decimal expansion. Now, let us go to discuss with the most generalized form of the pigeonhole principle. The pigeonhole principle states that there must be at least 2 objects in the same box. When there are more objects than boxes, however, even more can be said when the number of objects exceeds the multiple of the number of boxes. For instance, among any set of 21 decimal digits, there must be 3 that are the same. This follows because when 21 objects are distributed into 10 boxes, one box must have more than 2 objects. So, this is the meaning of most generalized pigeonhole principle. So, what you can infer is you have more than the number of boxes comes and we have more general ideas. If you want to understand this, before we have to understand what is the meaning of floor function and ceiling function. The symbol stands for a floor function, this symbol stands for a ceiling function. If you take a floor and ceiling function, give as the nearest integer up or down. For example, what is the floor and ceiling of 2.31? if you have a 2.31 here, the floor of 2.31 is 2 and the ceiling of 2.31 is 3. So, that is the difference between floor function and ceiling function. Keep it in mind this. Let us go to the generalized form of the Pigeon Hole principle. Pigeon Hole principle states that if n objects are placed into k boxes, then there is at least one box containing at least ceiling function n by k objects. That is, we have to prove by contradiction principle. Suppose that none of the boxes contains more than n by k ceiling minus one object, then the total number of objects is at most k into the ceiling function n by k minus 1 less than k into n by k plus 1 minus 1 equal to n, right. So, this way we can do that the inequality of the ceiling n by k is less than n by k plus 1 has been used. Therefore, this is contradiction that there are totally n objects, hence we can generalize the more in Pigeon Hole principle. Let us start with one example. 100 people, there are at least the ceiling 100 by 12. So, the corresponding value we have 9 who were born in the same month. So, this way we can do for what Pigeon Hole general principle in terms of the ceiling function. Next, what is the minimum number of students required in a discrete mathematics classes to be sure that at least 6 will receive the same grade? If there are 5 possible grades A, B, C, D and F. So, the solution to this problem is the minimum number of students needed to ensure that at least 6 students receive the same grade is the smallest integer n such that the ceiling of n by 5 equal to 6. Therefore, the smallest such integer is what n we have to find 5 into 5 plus 1 equal to 26. So, if we have only 25 students, it is possible for there to be 5 who have received each grade, so that no 6 students have received the same grade. Thus, 26 is a minimum number of students needed to ensure that at least 6 students will receive the same grade. So, this is the meaning of Pigeon Hole principle using the 5 possible grades, using at least 6 will receive the same grade. So, that with the help of the general Pigeon Hole principle, we apply the ceiling function ideas. So, we can receive the how many number of grade from the given set of possible grades. So, these are very good examples of general form of the Pigeon Hole principle. Next, one more example. How many cards can be selected from a standard deck of 52 cards to guarantee that at least 3 cards have the same suit are chosen? Another question, how many must be selected to guarantee that at least 3 hearts are selected? So, we have a solution. We have a standard deck of cards, 52 cards, and 13 cards having with 4 cards of each kind, one in each of the 4 suits, the hearts, diamonds, spades and clubs. So, these are all the well known idea of standard deck of 52 cards. Keep it in mind this, we have 4 boxes, one for each suit. As cards are selected, there are placed in the boxes reserved in 4 cards that suit. By method of generalized Pigeon Hole principle, if n cards are selected and at least one box containing the ceiling of n by 4 cards, and consequently we know that at least 3 cards of one suits are selected is the ceiling n by 4 is greater than or equal to 3. The smallest integer n such that n by 4 greater than or equal to 3 is n equal to 2 into 4 plus 1 equal to 9. So, 9 cards suffix. Note that 8 cards are selected. It is possible to have 2 cards of each suit. So, more than 8 cards are needed. Consequently, 9 cards must be selected to guarantee that at least 3 cards one suit are chosen. One good way to think about this to be note that after the 8th card is chosen, there is no way to avoid having a 3rd card of some suit. So, this way we can attack the problem of example 7a. Now, we have a second question, that how many selected card of 3 hearts to guarantee to get it. So, this is also we have to apply the generalized pigeonhole principle, because we could not do directly. Now, we are going to answer the example 7b. We could not apply the pigeonhole principle, generalized pigeonhole principle for the second question, because we want to make use that there are 3 hearts, not just 3 cards of one unit. Note that in the worst case we can select all the clubs, diamonds and spades, 39 cards in all, before we select the single hearts. Therefore, the next 3 cards will be all the hearts. So, we may need to select 42 cards to get 3 hearts. So, that is the way we can do for the second question. Whereas, the first question is easily solved with the help of a generalized pigeonhole, and second question we could not do that, but we can select all the clubs, diamond and spades consists of 39 cards. Therefore, the next 3 cards will be all hearts. So, 39 plus 3 equal to 42 cards to get 3 guarantee card of the 3 hearts are selected. Next example, suppose that a computer science laboratory has 15 workstation, 10 servers. A cable can be used to directly connect a workstation to a server. For each server, only one direct connection to that server can be active at any time. So, we want to guarantee that at any time any set of 10 or fewer workstation can be simultaneously accessed to different servers through direct connections. Although we could do this by connecting every workstation directly to every server and using 150 connection, what is the minimum number of direct connection needed to achieve this goal? This is a question. So, we have a 15 workstation and 10 servers, and we have to connect the workstation to the server. That is the first assumption. Now, the question is the minimum number of direct connection needed to achieve the goal is required. Now, we have a workstation, let it be W1, W2 and so on W15, and these having a servers, totally 10 servers. Therefore, let it be S1, S2 and so on S10. Suppose we connect Wk to Sk for k equal to 1 to 10, and the rest of them you call it as W11, W12, W13, W14 and W15 to all 10 servers. Now, you see there are 16 direct connection, right. Now, clearly 10 or fewer workstation can simultaneously access the different servers. Therefore, noting that the workstation Wj is included with 1 to 10, therefore, it can access server Sj, and for the workstation Wk, therefore, k greater than equal to 11 it is included. Therefore, we have a corresponding workstation Wj with 1 less than or equal to j less than or equal to 10 not included. So, Wk can access server Sj. This follows because there are at least as many available servers Sj as there are workstation Wj, with 1 less than or equal to j less than or equal to 10 not included. Now, suppose there are fewer than 60 direct connection between the workstation and servers. Some server would be connected at most 59 by 10 with the help of Pigeon general principle. So, 59 by 10 is 5.9, that is 5 workstation with the help of the floor, and then if all servers were connected at least 6 workstation, there would be at least 6 into 10 equal to 60 direct connections. This means the remaining 9 servers are not enough to allow the other 10 workstations simultaneously to access the different servers. So, consequently, at least 60 direct connections are needed. It follows that the number of things should be connected is 60. Therefore, 60 is our requirement of this connection. So, 60 direct connections are needed. Some more elegant application of the Pigeon Hole. During a month with 30 days, a baseball team plays at least one game a day, but no more than 45 games, so that there must be a period of some number of consecutive days during which the team must play exactly 14 games. Now, we have a detailed solution to this. So, let Aj be the number of games played on or before jth day of the month. So, in the month we have 30 days, let it be A1, A2, A3 and so on A30. So, this is in the increasing sequence of distinct positive integers, and we have a team plays at least one game a day, but no more than 45 games. Therefore, Aj may varies from 1 to 45, and after A1, A30 we have to A1 plus 14 and A2 plus 14 and so on. A30 plus 14 is also an increasing sequence of distinct positive integer with 15. So, which is less than or equal to Aj plus 14 less than or equal to 59, because the 60 positive integers of A1 to A30 and A1 plus 14 and so on up to A30 plus 14, totally it consists of 60. Therefore, these are all the balls less than or equal to 59. It means the pigeonhole principle of two integers are equal, because the integer Aj where j varies from 1 to 30 all are distinct. Therefore, the integer Aj plus 14 where j varies from 1 to 13 all are distinct. It means the indices I and j with ai is equal to Aj plus 14. This means exactly 14 games were played for the j plus 1 to day I. So, this is a way we can solve that, the elegant way of application of a pigeonhole principle with the help of the month and associated with the games. Now, we will move to the next problem. Show that among n plus 1 positive integers not exceeding 2n, there must be an integer that divides one of the other integers. First of all, understand that the numbers of positive integers not exceeding 2n. 2n mean even number. Say n we do not know, n may be even or odd, but generally given n plus 1 positive integer, but not exceeding 2n. Therefore, what we have to show that there must be an integer divides one of the other integers. See, we have what n plus 1 integer, let it be the sequence a1, a2 and so on, an plus 1 as a power of 2 times an odd integers. Therefore, we can rather write aj as 2 power k j into qj, where j varies from 1 to n plus 1. Now, kj is a non-negative integer and here qj is odd. Therefore, the integers q1 to qn plus 1 are all odd positive integer which is less than 2n. Now, there are n odd positive integer which is less than 2n. It follows that pigeonhole principle that two of the integer q1 to qn plus 1 must be equal. Therefore, there are distinct integer I and j such that qi equal to qj, right. Let q be the common value of qi and qj. Therefore, this possibility implies that ai equal to 2 power ki into q. Here aj is 2 power k j into q. Now, it follows that the ki and kj are one is less than the other and also they divides one another, implies if ki greater than kj. It means aj also divides ai. So, that is the meaning of what n plus 1 positive integer not exceeding 2n and that divides one of the other integers. That is the end of the pigeonhole. So, I will continue the following of the pigeonhole principle to the next topic.